Hey SS2 students, and welcome. Today, we're going to tackle a chemistry question that looks simple on the surface, but it's actually a classic puzzle, and, a real favorite on exams. Let's solve the electrical puzzle of salt.
I mean, really think about that for a second. It's the exact same stuff, right? Sodium chloride. So how on earth can it be a conductor in one state, but a total insulator in another? It just feels like a contradiction. And honestly, this is a spot where a lot of students lose marks, because the explanation has to be super specific.
All right, so let's dive right into this chemistry puzzle. We're gonna break it down piece by piece, so that by the end of this, you'll be able to explain it perfectly, no problem at all.
Now, this slide right here confirms something you probably already know, and you're absolutely right to think this. We know salt is made of charged particles. The sodium atom, Na, gives away one electron to the chlorine atom, Cl, which creates a positive sodium ion, Na+, and a negative chloride ion, Cl-.
And that right there is the heart of the whole puzzle. We've got positive charges, we've got negative charges, all packed into that little salt crystal. So, why doesn't it conduct electricity? It feels like it should. This tells us something really important. Just having charged particles isn't the whole story.
To get our answer, we have to zoom way, way in. We need to look at what's actually happening inside a solid crystal of salt. The secret, it turns out, is all in its structure.
You see, in a solid, these positive and negative ions are locked into the super-organized, really rigid structure called a crystal lattice. Think of it like a packed movie theater, where every single person represents a charged ion. They're all there, but they're stuck in their assigned seats, held in place by these powerful forces. We call them electrostatic forces. They can't just get up and wander down the aisle.
So here's the most crucial point. In that solid crystal, the ions are definitely present. But, and this is the big but, they are not mobile. They are totally locked in place. Sure, they can vibrate a little bit, but they can't move from one place to another. And if your charge carriers can't move, well, you can't have an electric current. It's as simple as that.
Okay, so if the big problem is that the ions are all locked up, what's the solution? Well, it's gotta be to set them free, right? And lucky for us, in chemistry, we have two really good ways to smash that rigid crystal lattice and get those ions moving.
And this slide shows us those two methods. Over on the left, we've got melting. If you heat that salt to a super high temperature, the heat energy basically gets strong enough to overpower those electrostatic forces. The whole lattice just breaks apart, and boom, the ions can finally move around freely. Now on the right, we have dissolving. When you drop salt into water, the water molecules swarm the individual sodium and chloride ions, kind of shielding them from each other and plucking them right out of a lattice.
So whether you use intense heat or you use a solvent like water, it doesn't matter. The end result is exactly the same. The ions are now free to move. They've been liberated from their fixed positions in that crystal.
All right, so the ions are mobile. Great. But so what? How does that movement actually create an electric current? This is the final and maybe the most important piece of our puzzle.
First things first, let's give this a proper name. Any liquid or solution that has these mobile ions floating around is called an electrolyte. So that means molten salt is an electrolyte, and salt dissolved in water, what we call an aqueous solution, is also an electrolyte.
Now this diagram shows what happens when we put our electrolyte to work. If we stick two electrodes into it and hook them up to a battery, we get a positive electrode, the anode, and a negative one, the cathode. And you know the rule, opposites attract. So the positive sodium ions, the Na+, they start moving towards the negative cathode. At the very same time, the negative chloride ions, the Cl-, they move towards the positive anode. And there it is. That's the big aha moment. In an electrolyte, the electric current isn't a flow of electrons like you see in a metal wire. No, it is the physical movement of the ions themselves through the solution. This organized parade of positive charges moving one way and negative charges moving the other way, that is the electric current.
So let's pull all of this together into a really clear comparison. Honestly, this is the slide you'll want to have burned into your memory for your exams.
Just look at this table. In all three states, solid, molten, and aqueous, are the ions present? Yes, yes, and yes. That never changes. But now look at that next column. Are ions mobile? For the solid, it's a hard no, and that's why it can't conduct. For molten and aqueous, it's a yes for both. And that, right there, is the single deciding factor. That's what turns on the switch and lets them conduct electricity.
So if you take away just one single thing from this whole explainer, please let it be this.
It is not enough for ions to just be present. They absolutely must be mobile, free to move and carry that charge from one place to another.
Okay, now it's your turn. Let's see if you can apply this logic yourself. Remember, those WAC and NICO exams love to ask you to explain things, not just spit back facts. So let's put your reasoning to the test.
Here is your challenge. Lead-2-bromide is another ionic compound just like salt. Using the ideas we've just gone over, I want you to explain why it behaves the exact same way. Go ahead and pause here and really try to build your answer. Make sure you use those keywords: crystal lattice, fixed positions, strong electrostatic forces, and of course, mobile ions. Start by describing what's happening in the solid state, and then explain the change that happens when it melts. You've got this.